Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a privilege and pleasure to introduce Glenn Schaefer to you. And I will not repeat the abstract or his life story. He's very famous in Foundations of Probability. I want to say a word about foundations. Most people are not interested in foundations. And in a sense, it's a success that you can forget about foundations. But some people are interested. So in particular, Kolmogorov, who wrote the famous axioms, were not satisfied, and then returned repeatedly to the issue, developed Kolmogorov complexity and other approaches to various approaches to what probability is. But Glenn is a professional
in foundations
in the field, and so I'm looking forward to hear your opinion.
Oh, thank you. Well, it's an honor to be invited by Yuri and have the opportunity to talk to some smart people on this subject of, as Yuri says, I'm kind of a professional of the foundations of probability, which has also got me interested in writing about the history of probability, because I really believe that you can't contribute unless you take seriously what people before have done. And a lot of what people do does not take very seriously what came before. We kind of have there is a tendency to kind of caricature what people before thought to prove your own point of view is smarter or something. And what I'm doing, he mentioned Kolmogorov and complexity. These ideas have some roots in this, and they're very much based on my recent work, that is the last 10 years, with Vladimir Vovk, who was one of Kolmogorov's last students. Didn't actually finish with Kolmogorov, but started with him. And Vovk's idea, again, not just starting with him, but really made very crisp by my colleague Vovk, and in the book I wrote together with him in 2001, was that we can mathematically, we can replace measure theory by game theory as a foundation for probability. And the idea, what good is this? The idea is it opens up some generalizations and some applications, but also a different way of understanding this philosophical meaning of probability, the idea. So, the abstract made this sort of basic points. We're really saying a mathematical framework. So whereas in measure theoretic probability, where does the measure theory come in? One place the measure theory comes in is that you prove certain things are going to happen by proving that they have high probability, or that they have probability 1. So how do you replace that idea of measure 1, except on a set of measure 0? What do you replace that with? And in this game theoretic approach, you replace it by the idea that if the event doesn't happen, a gambler will get infinitely rich, or will get very rich. Infinitely rich is like probability 1, very rich is like very high probability. It's because gambler, if you're playing in a fair game, you're not supposed to get very rich. Now, getting very rich, we make it a little more precise. Multiplying your stakes, multiplying the capital you risk by a large factor is what we mean by getting very rich. George Soros got very rich. There are some other people in business and finance who get very rich. Almost invariably, they do that by risking someone else's money. They didn't just take a certain amount of money that they had and multiply it by 1 million. No, they borrowed somebody else's money and multiplied it by 10. And took a big share of it. That's how they got rich. So what's much less believable is that somebody in a fair game would multiply the capital they risk by a large factor. So that's what we take as in game theory is replacing the idea of a small probability or a zero probability. But the technical picture that emerges also turns out to help us with the idea of forecasting. If you do know my name, of course, you know that about the Dempster-Schaeffer theory. So part of my talk would be to take these newer ideas and try to relate them to the subjective probability ideas. I think this slide actually says about the same things as the previous slide, except I say it a little differently here. On the previous slide, I said that the classical theorems are proven by betting strategies that multiply the player's stake by a large factor if the prediction fails. So this is kind of looking at it from the mathematical point of view. Now I say the same thing from a philosophical point of view. So philosophically, the question is, what does probability mean? Here what I'm saying is what probabilities mean is that probabilities are prices. And when we say that these probabilities are valid or correct or they're the right prices, what we mean is that somebody buying at those prices, gambling at those prices, is not going to multiply the capital they risk by a large factor. That's our concept of validity, of the meaning of probability, or empirical concept. If you want to make it into, I was talking with Bernie here about Bayesian subjectivist and objectivist interpretations of probability. You could give this an objectivist or a subjectivist interpretation. If you say nobody's going to make a lot of money with these at these prices, you could say that's really true. That would be an objective interpretation. Or you could say I think it's true. That would be a subjective interpretation. So somehow this point of view brings those two together in kind of a trivial way. The applications, I probably won't have time to talk about all these, but there is a new forecasting method that comes out of it, and there are applications to finance. And more recently, I'm currently working on a betting interpretation of subjective probabilities. So these are the references. It really started with a book. Well, Vovka and I worked on this book starting about 1995, 96. So it took us 5 years to write it, but it's already 7 years old since it came out. And since then, we've written a lot more, and the working papers that we have on this topic are all at this website, and we've published a few of them. It's kind of hard but the stuff in finance, the finance people are very conservative. It's the very hardest place I ever found to publish, ever ran into. So who are our heroes? Pascal. We could start with Pascal because, again, we were with Ite and Yuri. I was talking about this at lunch. We were talking about this about Pascal and Fermat. People often say that Pascal and Fermat is where probability theory started. And you could actually think of Pascal as doing it game theoretically, and Fermat as doing it measure theoretically. So that's kind of an anachronistic way of seeing it, reading these categories back into the beginning. But certainly you could give Pascal some credit for thinking about probability game theoretically. As a matter of fact, I'm teaching introductory probability to graduate students in the business school at Rutgers right now. And the textbook I'm using, like all the textbooks, do it measure theoretically. So I give you an example. How do you find out the probability? How do you prove? Let's say you're tossing a biased coin. So it's not 50-50. How do you calculate the probability of getting two heads before you get two tails? That problem is in the first chapter of the textbook I'm using. And the author goes to a great trouble to show how to solve it combinatorially. which fits it into the major theoretic framework we use for probability. If you think about it, it can actually be solved more easily by Pascal's method. So I'll skip over these two guys, and I skipped Pascal. I took Pascal's slides out. The Pascal slides are not in this, are not here. There must be a marker? No. In Microsoft, you don't use a marker. You just use your PowerPoint. Is that right?
Yes, you can write here, but
Oh, there. They're behind the slide. They're behind the screen. I took this out of my slides because I thought, oh, I won't do that. But Pascal, there was this question. Pascal and Fermat were discussing the following question, the problem of points. You're playing a game where you play a number of rounds. Maybe you're just tossing a coin, heads or tails, fair game. Or maybe you're playing tennis or something. You have a number of rounds, and you've agreed it's like a tournament. The first person that wins a certain number of rounds wins the game. And they also win the stakes. So I put $50 down, Yuri put $50 down, the stakes are $100. But now he wins if there's, if he gets one more point, he wins. But I need 2 more points to win. So the question is, if we stop now, how should we divide the stakes? And everybody knows the answer nowadays. The answer is Yuri should get 3/4. Because if we kept playing, he would have a 3/4 chance of winning. And I should get 1/4. Everybody knows that, but in the time when Pascal and Fermat were exchanging their letters in 1654, nobody knew it. If you read Cardano's book, you would have thought the answer was 2/3. Fermat solved this by saying, if you played 2 more games, the winners could be Yuri could win both games, or Yuri could win the first, and I could win the second, or I could win the first and Yuri the second, or I could win both. Yuri only needs 1 more point, so if any of these things happen, 3 out of 4, he wins. So his probability is 3/4. That's the way that's the way Fermat solved it. But Pascal didn't like that answer, or at least it's not the one he thought of. And anyway, he didn't like it either when he saw it. He said, this doesn't make sense, because if Yuri wins, he's not going to play another game. He only needs 1 point. So these don't make any sense. We're not going to play 2 games. So Pascal analyzed it in a way. Here we go. Pascal did the story game theoretically. He thought about it this way. He said, we play the first game, and either Yuri wins or Glenn wins. If Yuri wins, we stop, and Yuri gets $100. If Glenn wins, we play another game, and either Glenn wins or Yuri wins. And if Glenn wins, Glenn gets the $100, and Yuri gets, let's see, no, we're putting down here the amount that Yuri gets. If Glenn wins, Yuri gets 0. If Yuri wins, he gets $100. So the way Pascal thought about it, he says, what about if you're in this situation? You've got even chances of getting, Yuri's got even chances of getting 0 or 100, so he deserves 50. So if you're in this situation, he's got even chances of getting 100 or 50, so he deserves 75. That's how he got the 3/4. And this is the game-theoretic solution, and it doesn't involve taking that step that you're really not going to take. And I say there's lots of harder problems like this that are in probability textbooks, but very seldom in our probability textbooks do we solve them this way. We try to fit them into this combinatorial picture because that's measure theory. I shouldn't have got into that, but I'm teaching I'm teaching standard probability theory, so I actually find myself saying these things. My other 2 heroes are Antoine Cournot, who was the Frenchman who first enunciated this idea that the only way that probability makes a contact with the world is through probabilities that are close to 0 or 1, as already mentioned. And then John Veal is a guy I'm writing a biography of right now, a French mathematician who died in, I said 1989, didn't I? But I've got 1988 here. I'm not sure which is right. But 1910 is right. I think he actually died in 1989. He's the one that proved, I'll show you a theorem he proved, the kinds of approach I'm taking to probability theory he actually did in 1939. This is Pascal's statement, this is Cournot's statement. In his book on probability and statistics in 1843, he used a different language. He was a Kantian, of course. I mean, he lived at a time when Immanuel Kant was a very influential philosopher, and you didn't talk about the real. Immanuel Kant did not talk about the real world. Immanuel Kant talked about phenomenology. That's what you actually could see was the phenomenon. You never knew what was really there. You could only see the phenomenon. So empirical, what we might say empirical or real, he said phenomenological. And he said the only thing that gives an objective and phenomenological value to the theory of probability is its predictions that something is going to happen, that namely, its prediction that something has probability that's infinitely close to 1 or not happening has probability infinitely small. You know, infinitely small, you gotta, this guy was French. Even in the following century, when the French said infinitely small, they didn't mean what you mean by infinite. Infinitely small meant very, very small. So Cournot had two favorite examples of something that was, the probability of which was infinitely small. One example is you have a cone and you try to balance it on its point. I guess I have a cone. So you try to balance it on its point, and it's not going to stand up. Even though mathematically you could balance it perfectly to stand up, it's not going to happen. The second thing, his second favorite example was a tile falling off. You know, the French had these, all their roofs were these red tiles. So his other example was that you're walking down the street and a tile falls off and hits you in the head. That could happen too. It's not going to happen. It's not going to happen. That's a negligible probability. So that was his other example of an impossible event. But, you know, I don't know, is it probability 0? But it's infinitely small. It's what he called infinitely small. Veal was the one who put together this idea of infinitely small probabilities and the idea of multiplying your capital by a large factor. So he showed that really in sort of standard probability situations, they're equivalent. Why are they equivalent? Well, that's Markov's inequality. This is a mathematical theorem. Mathematical theorem that was proven by Markov that says that if you have a non-negative random variable, that means if you have a non-negative random variable, think of it as a payoff that you buy. What is the price of that payoff? The price of that payoff is its expected value. So if your gamble is to buy that random variable, the expected value is the stake that you start with. And if that random variable can't be negative, so being negative means you have to pay the money. That would mean you've lost more than the stake you paid in the first place. That's what we're not allowing. So if you play in such a way that the outcome is positive, then the probability of multiplying the expected value by 1,000,000 is less than or equal to 1 in 1,000,000. That's Markov's theorem, and it's obvious that you're going to go the other way too. If you have a probability of an event of very small probability, if the probability is 1 in 1,000,000, then betting on that event will turn $1 into $1,000,000. So it's obviously if and only if. So in that sense, Veal's statement that an event of probability 0 not happening is equivalent to you're not making a lot of money, that's a triviality. It's just Markov's theorem, which is easy to prove. But Veal applied it, used the idea, well, he advanced the idea from the situation where you buy a single random variable to a situation where you have a strategy in a probability game that goes for many rounds. So here is an example of the kind of game that Veal used. Now, in this case, we could have a game that goes for an infinite number of rounds, or we could have one that stops at some predetermined time, or we could have some other kind of stopping rule. On this slide, I assume that we pick some big number, n, capital N, and we play for capital N rounds. And here's the general form of the games that we talk about in our theory. The general form has 3 players: forecaster, skeptic, and reality. So forecaster announces prices. Skeptic decides what payoffs to buy at those prices. And reality decides what happens. This K0 is the capital of skeptic. Skeptic is the gambler. Why do I call him skeptic? Because I think of skeptic as testing the forecaster. That's the original idea of skeptic. So in this theory, in standard statistics, we do statistical testing by looking for an event that would have small probability under the theory we're testing. Here we test by trying to beat the theory, betting against it. The person doing that skeptic, we could call him we could call him the investor. The investor is trying to beat the theory that the stock market is efficient. We could call him gambler. On this slide in our book, we called him skeptic. We could call him statistician. He's doing the testing. But then maybe the forecaster might be a statistician too. So that's not necessarily the best choice. Veal showed that any test of forecaster can be expressed as a betting strategy for skeptic. That's a little vague. Let me be a little clearer. Veal didn't actually have a forecaster in his games. Veal assumed there was some probability distribution that you're using to give the forecasts. But in our book, and it was Voff's idea, we generalized this so you actually could have a forecaster who doesn't necessarily use a probability distribution. Now, I don't say it on the slide, but maybe I should introduce the idea of what a probability distribution is in this kind of a situation. If you go back to here where you have a number of rounds, n rounds, the player here who we think of as nature, that's reality. Reality is determining a sequence of outcomes. So if the usual way of thinking about a probability distribution would be a probability distribution for what reality does. So if we call reality's moves x, reality does, first move is x1, his next move is x2, and so on up to x capital N. We would have a probability distribution could be thought of as governing what reality does. But that's not the way we think about it here. A probability distribution for this sequence of outcomes. The way we think about it here is we think about this as a strategy for forecaster. Because for this probability distribution on this sequence, it would give probabilities for x1. And so it would give prices for any payoff that depends on x1, expected value of that payoff. So that would be forecaster's first move. The prices he would give would be the probabilities for x1. On the second move, he would look at what x1 already happened and give the conditional probabilities for x2 given x1. And so on and so forth. The next one would be the probabilities for x3 given x1 and x2, and so on. So forecaster could use a probability distribution in that way to define a strategy for his moves. And from our game-theoretic point of view, that's really all a probability distribution is. A probability distribution for reality's moves is a strategy for forecaster. And that's the role it plays in our game. So we could start with a strategy for forecaster and say forecaster is going to follow this strategy. And if we do that, forecaster is no longer a player in the game. We can take him out. We know what he's going to do. We just have skeptic and reality playing against each other. And that's what Veal did. Veal, as I say on the next slide, Veal didn't really have a forecaster in his game. He had a known probability distribution in his game. So we've generalized this by having this idea of a forecaster who doesn't necessarily have to play by a strategy. You can play a game without having a strategy, right? People do it all the time. They just do what comes into their mind when they get there. They don't have a plan for what they were going to do before. So this is an example of what we're talking about. I've been kind of vague and philosophizing. This slide actually states a theorem in game theory. And the theorem is the game-theoretic version of one of the simplest and best-known theorems in probability theory, proven in 1909 by Emile Borel. It was the first version ever proven of the strong law of large numbers. The strong law of large numbers says if you play with a fair coin and you toss it an infinite number of times, that the fraction of heads, you toss it 100 times, you've got 53 heads. You toss it 1,000 times. After 1,000 times, you got 504 heads. You keep on going. The fraction of heads will converge to 1/2. That's what Borel's theorem says. Borel's theorem says the fraction of heads will converge to 1/2 with probability 1. Or to put it a different way, the fraction of heads will converge to 1/2 except on a set of measure 0. If you ever taught probability theory, you got to. So what does that mean except on a set of measure 0? What does it mean? It means it converges to 1/2 unless it doesn't. There's a lot of sequences that don't converge to 1/2. A lot of them, infinite number. In some sense, almost all of them don't converge to 1/2, except except under this probability distribution, they have measure 0. So what does that theorem mean? You kind of have to pound it into people's heads. You kind of intimidate them into agreeing that if you prove that something is true except on a set of measure 0, you've proved it. So we're replacing that set of measure 0 with a different concept. We're replacing the measure-theoretic concept of converging except on a set of measure 0 with the game-theoretic concept of converging unless the skeptic gets infinitely rich. Replacing the measure-theoretic idea with a game-theoretic idea. But here's precisely how we do it. Here's the game. I'll be skeptic. And Bernie can be reality. So what I do is I start with $1. And we're going to play forever. I don't put any capital E in there. We're just going to play forever. And skeptic, that's me, I bet. My bet can be any number. It could be $5, minus $5, 5 cents, 0.05. I give any number, and that's my bet. I'm going to bet, if it's a positive number, I'm betting on heads. If it's a negative number, I'm betting on tails. Bernie says what happens. 0 for tails, 1 for heads. And if I said $5, what happens? Well, if I say $5 and he says heads, I get $2.50. If I say $5 and he says tails, I lose $2.50. So actually, in this particular formulation, in this way of setting it up, the number I give as skeptic, as the bettor, I'm announcing the total stakes. I put down half of it. My opponent puts down the other half, and winner takes all. That's the mathematical setup. But the idea is this is a perfect information game. We play in order. We play in the order given. I move first. I announce my move. Bernie knows whether I bet on heads or tails. He knows how much I bet. And then he decides whether I win or lose. And then we do it again. That's the first one, the second one, the third one. And it's a perfect information game. We see what's going on. So Bernie can make sure that I always lose. That I lose money. He can be sure of, he can make me lose money every time. That's up to him. But what are the rules of winning the game? We win the game. Well, if I only start with $1, so I better not bet $5. Because if I lost $5, or if I lost $2.50, I'd be out of the game. So I'm not allowed to if my capital becomes negative, because what we do is each time we add the profit to the previous capital. If my capital becomes negative, I lose the game right there. It's over. But otherwise, we keep playing, and I always, if I'm smart, the rules of the game don't say I have to avoid this happening, but if I'm smart, I don't let this happen. I never bet, I only bet 5 cents when I start. I only bet a fraction of what I have so that my capital will never become negative. And there's 2 ways I win. I win if Bernie converges to 1/2. He's saying 0, 1, 0, 1. If he averages out to 1/2, in other words, half the time he says heads, half the time he says tails, I win. Or if I become infinitely rich, I win. I win either way, those 2 ways. And the theorem says I have a winning strategy. I can win. He can keep me from ever winning a cent, but if he does that, I'm going to play in such a way that he has to converge to 1/2. To keep me from winning if he's going to constantly make me lose, then I can force, if his idea is to always make me lose, then I have it in my power to determine exactly what he does. And I'm going to do it in such a way that he has to converge to 1/2. And in fact, I can play in such a way, I have a strategy that will mean that he cannot avoid both these things. If he keeps me from getting infinitely rich, he's going to converge to 1/2. If he avoids converging to 1/2, he's going to make me infinitely rich. That's the theorem. And the theorem, I will show you a proof of this theorem. It's not hard to prove. We actually say what the strategy is. Constructive proof. But this is sort of analogous. It can be thought of. There's other proofs you can give which are analogous to the standard proofs in the textbooks that measure theoretically. So the measure theoretic proofs all involve taking measure theoretic proofs of these kinds of asymptotic theorems, where you look at limit theorems. The measure theoretic proofs generally involve looking at sets of measure 0 and taking unions of them. If you take a countable number of sets of measure 0, it still has measure 0. So you take unions of sets of measure 0. That's basically what the proofs are all about. In the game-theoretic approach, what we do instead is you average strategies. Instead of taking unions of sets of measure 0, you average strategies. So if I have a strategy that will make me rich, if Bernie does one thing, and I have another strategy that will make me rich if he does something else, what do? Instead of playing my dollar on one of those 2 strategies, I play 50 cents on both of them. And multiplying 50 cents by infinity is just as good as multiplying $1 by infinity. And that means that that means I've averaged the 2 strategies. When I put 50 cents on one and 50 cents on the other, it means that whatever the one strategy said and whatever the other strategy said, the strategy is a number. The strategy tells me to choose a certain number here. So I just take the average of the 2 numbers. That's averaging the 2 strategies, putting 50 cents on one and 50 cents on the other. So I can do that only with 2 strategies, but I can do it with a countable number of strategies. And I don't give them all equal weight, obviously. I give 1/2, 1/4, 1/8, whatever. But turning any of it into infinity gives me an infinite. So I can take an infinite. So if I have a strategy for this that makes me infinitely, so that's the kind of technique of proof. But I think I've got a different proof for you. This is the actual proof that Veal suggested in 1939. So, our book is like revealing this to the world in 2001. And there had not been any. It's very nearly true that nobody read the book after 1939. Not quite true. Doob read it, but after Doob, the American mathematician Joseph Doob, after Doob ever read Doob, nobody read Veal, and Doob was off in a different direction. So I do know a couple cases. I do know one case. Herb Robbins wrote a paper in the 70s, and as a footnote to the paper, it's obvious that somebody, after he'd written the paper, somebody said to him, Veal already did something like this. In a footnote to Robbins' paper, he has a reference to this. That's the only reference I know to this after 1939. Well, Borel had some other kinds of references, but not to this particular theorem. This is the strategy. What is a strategy? It tells you what you bet, tells you that move as a function of the other player's previous moves. And this is what the function is. Rn, this is the number of ones so far, the number of heads so far. So Rn minus 1 divided by n minus 1 would be the fraction of heads so far. The number of heads so far should be about 1/2 of the trial so far. So if there are too many heads, if there are too many heads, you're going to make Sn positive. It's going to be this fraction of your capital so far. You only make it a small fraction of your capital so far. But it's going to be positive if you have too many heads so far, more than half of them are heads so far, you're going to make this bet move positive, which means that you're going to win if he continues to have too many hits. To keep from your winning, he's going to have to move back sooner or later to less heads. That's the basic idea. Now, that's a simple enough formula. And just by a simple recursive calculation, just sit down and try it, you can easily derive this formula as the formula for the capital at time n. This will be your capital at time n, depending on what your moves are so far. It only depends on the previous, it only depends on, the capital only depends on reality's moves through the number of heads that he does. So this defines a capital process. So in this kind of game, a capital process for skeptic is a function that tells how much money he has at every round, depending on how the reality moved. Okay, so Veal invented a word for capital process. He coined a term for capital process. Does anybody know what the name is? Yuri does, because I told him this afternoon already. He called it a martingale. That's how the word martingale got into mathematical probability theory, because Veal adopted it as a name for a capital process. Where did the word martingale come from? That's always a little nidbit of information. The word martingale was previously used for to mean a betting strategy, and it was actually used to mean a wild betting strategy, the betting strategy where you double your bet until you win. So, many people, many amateur naive gamblers come up with this idea. They do a little arithmetic calculation and say, if I double my bet every time I lose until I finally win, I always end up winning. Because I'll cover if I double the bet every time, I'll cover all my losses and still win something. That is, if you can keep doubling your bet every time. There's a little town on the Mediterranean in France named Martigues. And martingale means in the fashion of the people in Martigues. So there was ways of dressing a la martingale, there's ways of sailing a la martingale, and there's ways of gambling a la martingale. And the martingales were kind of wild people, apparently, according to their neighbors. So that's what the word martingale came from. So it was natural for Veal to use the word martingale for a strategy. But then he said, mathematically, knowing the strategy is equivalent to knowing the capital process. Once I know this, I can calculate this, and once I knew this, I could from the capital process, I could deduce what the strategy was. So it's mathematically the same thing. So I'll use the word martingale to mean a capital process. So that's the original mathematical meaning of the word martingale until Doob took the theory over and turned it into something in measure theory. In game theory, martingale just means capital process. That's all it means. Now, this particular capital process, you can read my slide. You've already read it. You've got some factorials there. So you expand the factorials by Stirling's formula, and you apply the Kuhlbach-Leibler inequality, and you find out that if this is bounded, then the fraction of heads has to converge to 1/2. So if the capital remains bounded, the fraction of heads has to converge to 1/2. So one of the other things has to happen. Either this converges to 1/2, or the capital process diverges. Now you might say there's a little piece not there. If you're thinking about this mathematically, it wasn't enough for the capital process to diverge or to fail to be bounded. We wanted the capital process to go to infinity. We wanted the guy to get infinitely rich. And all we've proven is that it's going to be unbounded. Either the fraction of heads is going to converge to 1/2, or the capital is going to be unbounded. So how can you turn the capital being unbounded into getting infinitely rich? And actually, that's not hard. Because if you know the capital is unbounded, you can say, okay, when it gets to 1 million, I'll stop. And then, or let's make it easier. When it gets to 1, well, I started with 1. Okay, when it gets to 1 million, I'll stop. And then I'll start playing the game again. Because I know it's going to get to 1 million again. And I just keep doing that. From it being unbounded, you can get, that's a trick in probability theory. That's a trick that trick is in measure theory too. Turning something unbounded. The Doob used that trick, but it's already in Veal.
What if it's unbounded but negative?
No, it's this is a positive number. But that's the part of the trick. I mean, it's important that this is a positive number. Because the requirement of the game, I'm trying to prove there's a winning strategy. And if Kn ever becomes negative, I've lost. So part of the proof is observing that this is always positive. Yep. Which means that to achieve that, I sometimes have to bet very tiny. I mean, it may take a long time. This may be my gains may be very slow coming. I've got infinity to work with here. There are finite versions of this. Just like there are the so-called weak law of large numbers are finite versions. You only have a finite number of rounds. The winning is going to be that you get very rich, some constant C, or you get within a certain range of 1/2, and then you're going to have a winning strategy if you play enough rounds, which is going to depend on how rich you want to get and how close you want to get to 1/2. This is the same bound you get from Chebyshev's inequality when you prove the weak law of large numbers in a probability theory. So everything, we just do the usual stuff, but it becomes game theory. Veal did not confine himself to the case of 1/2. He looked at the general case where you could start with any probability distribution P for the sequence of reality's moves. I called them X's over there, but here I'm calling them Y's, reality's moves. In that case, what is the payoff going to be? We have the same setup here, but now the payoff is going to be the total stakes times not Y, and not the 0, 1 minus 1/2, but the 0, 1 minus the conditional probability of a 1 given the previous moves. This will be what the prices are, what the probabilities are. And then the next move after that is to introduce a forecaster. I mentioned earlier that in the general case there's a forecaster that gives the probabilities instead of a probability distribution that gives the probabilities. So in this case, again, the payoff is going to be the 0 or 1 minus the probability times the total stakes. And the theorem is going to be that the convergence is going to be the difference between the zeros and ones, the difference between the fraction of heads, which is the average of the yi's divided by n is the fraction of heads, the fraction of ones. Difference between that and the average probability is going to converge to 0. That's the law of large numbers in this case, where the probabilities can be arbitrary. And the same theorem works, the same proof practically, really the same proof works. And this is getting us outside the classical framework of probability theory because there's no probability distribution. You don't start with a probability distribution. You have a probability for every step. But a probability distribution is more than that. A probability distribution tells you not just what the probability was on the 100th trial, but it also tells you what the probability would have been if reality had done something different on the first 99 trials. That's a lot more information. There's a lot more information in the probability distribution. A joint probability distribution for all the trials has a lot more information than just the sequence of actual probabilities. So there's a lot less information going on here, and yet you still get a skeptic having a winning strategy. This was the idea of there's a statistician colleague that someone that Vofk and I know very well Phil David, who was at the University of London for many years and is now at Cambridge, I think. He recently moved. But he had he published some papers, an idea which had some influence in statistics called frequential statistics for sequential prediction. And he was interested in this setup, even though he wasn't doing game theory probability quite the way we were, but his ideas were an ingredient in what we were doing. His ideas was that you should be able to do statistical testing without having a whole probability distribution. You should be able to do statistical testing based just on what the predictions are. If you have some statistical method for making predictions, you should be able to test those predictions even without knowing what predictions the system might have made if something different had happened. You should be, what difference should that make? I mean, that was his idea philosophically. What difference should it make what this guy would have said, or your theory about what he would have said if something different should happen? We should just test him on what actually happened. So this makes that, implements that idea, because we don't even bring in any theory about what he might have said. We just have what he actually said, and we have a way of testing him. Our way of testing him is trying to get rich. If we get rich without risking bankruptcy, if we multiply our initial capital of 1, which is all the capital we risk, if we multiply the capital risk by a large number, we've tested him and we've proved he's wrong. If we try to do it and we don't succeed, then he's passed the test, and he's making good probability forecasts or other forecasts. I probably have about 10 more minutes. What's the usual? So maybe I'll skip over, though I might say something about this slide, because Yuri mentioned that one thing I had said about in advertising this idea is that you don't really start with probabilities. The probabilities emerge from the theory. And in a sense, the way that works is this. Now, these probabilities here, you could say that the forecaster is giving probabilities, but actually the forecaster, we can generalize this to examples where the forecaster is not really giving probabilities. This example is the case of a 0-1. So you can't do anything without giving a probability if it's a binary outcome. But if it's in more complicated outcome spaces, you might not give a complete probability distribution. You might only give a price for some payoffs. So there might be forecaster might offer only some gambles. He might price only some gambles, and then skeptic would have to choose among those gambles. So we could still be testing skeptics' prices. But then we can get out of that. If we have this kind of a setup, we can define the idea of a sample space. What is the sample space? If we're just playing between skeptic and reality, the sample space is a set of possible moves for reality. But here skeptic is playing against two opponents, forecaster and reality. So the sample space would be the sequence of moves, the possible moves by his opponents, forecaster and reality. So the moves by forecaster and reality are P1, Y1, P2, Y2, and so on. The P's are any real numbers between 0 and 1. The Y's are either 0 or 1. So the total sample space is the 0-1 interval times the pair 0-1 to the nth power, if we're only making nth moves. That's the sample space. If you know probability theory, you know that a random variable is a function on the sample space. So the kinds of things that we would want to give prices to, or what you would call a random variable in standard probability theory. I don't want to call it a random variable because that implies we've got a whole probability distribution. But maybe I could call it a variable. Anyway, what it's going to be is a real valued function on the sample space. And I can define for the real valued function on a sample space an upper price. And I could also define a lower price. What is the upper price? The upper price is the least amount of money I would have to start with in order to get that payoff in this game. It's the smallest amount that I need to start with in order to have a strategy, because here alpha is and the way I set up here, alpha is my initial capital, not 1. So alpha is some positive number. So what is the smallest I can make alpha and still have a strategy to make sure that at the end of the game my capital exceeds that random variable, or that variable, which depends on the moves of my opponents. It's this is the amount of money it would take me to reproduce that payoff. In finance, we talk about replicating the payoff. So it's the least amount of money it takes me to reproduce it. In a sense, I would be, as a skeptic, I could afford to sell you the payoff at that price. So it's my least selling price. Going the other way, you might ask, well, if that's your least selling price, what's the most you would offer for it? What is your highest buying price? That would be the lower price. Since buying is the opposite of selling, when you buy something, you're just selling minus that. And the exchange, what you're paying for it, also has a minus sign in front of it. So just conceptually, by definition, the highest buying price would be 1 minus the lowest selling price for minus that. And this number is going to come out smaller than this number, smaller than or equal to. You may not be, because not everything is priced. If not everything is priced, in this game everything is priced. But if you have a game with more complicated outcome spaces where not everything is priced, there may be some distance between the most you would pay for it and the least you would sell it for, because these prices with the idea that you can buy it for that or sell it for that without risking any loss. You might actually end up with something left over, but you're sort of riskless. In finance, you're an arbitrageur. You're not taking any risks yourself. There's a special case of that. Of course, we're accustomed to the idea that the probability of an event is the expected value of the random variable that is equal to 0 if the event fails and 1 if the event happens, the indicator value. So once we have a concept of upper and lower prices, we've got a concept of upper and lower probabilities. And that's the same thing. So for events concerning, so we get upper and lower probabilities for the events concerning what the opponents, forecaster and reality, do in the game. So in this previous slide, in this example, we're going to get infinitely rich, which means that we can, that event is going to have a upper price that is as close to 0 as you want. In other words, the upper price is going to be 0. Now the lower price is less than or equal to the upper price. And if this one is very close to 0, this is bigger than 0. So if this one's very close to 0, this is going to be close to 0 too. So saying the upper probability is close to 0, you can just say the probability is close to 0. So we're, in a sense, this theorem also says, from a game-theoretic point of view, this says the game-theoretic probability of this event is close to 1. So we do get concepts of upper and lower probability, upper and lower price coming out of the game. So it's the idea of the probability. You don't put probabilities into the game, probabilities emerge from the game. And my time is basically up, right? So the applications, so I'll take 2 minutes to say something about what the applications are. This is something that came up after we wrote the book. After we wrote the book, we stumbled on the fact that we could actually use, you see, our book, we were concerned about, we got these 3 players. In our book, we were concerned about strategies for skeptic and strategies for reality. Strategies for reality are well, no, we weren't concerned. We were concerned in our book about strategies for skeptic, because strategies for skeptic prove the classical theorems of probability. So you could say there's not really too much new in our book. There is, but in a sense there's not. because we're just proving the same theorems. We're just taking the standard theory and putting it in a different language. And you got to kind of be, if you're interested in something substantive, that's not so interesting. We did generalize in certain ways. There are some new things because we generalized to the case where you don't have complete probability distributions. But this is a completely new idea. What about a strategy for forecaster? If we're looking at this game theoretically, how do we make good strategies for forecaster? And our idea was, we've got these strategies for skeptic. And we can average the strategies for skeptic. So if we want forecaster, skeptic is testing forecaster. This test here is a very weak test of forecaster. Here we just want forecaster's average probability to match up with the overall frequency of heads. That's actually not good enough. We would like something a lot more than that. If you think about the literature on testing forecasters, this is something about calibration. There's a literature on testing forecasters. One of the things you would like to have is you want more than the average of the forecaster's probabilities to match up with the frequency the event happens. A forecaster, if it rains here 80% of the time, then the forecaster could just say 80% every day, and he would pass this test. But you want more than that. You want him to be right on average during the spring and right on average during the summer. You want him, if you look at the times when he says 30%, you want it to rain 30% of that time. These things are called, having it rain 30% of the times when you say 30% is called calibration. Having that be true in the summer and the spring and not just overall is called resolution. So you want these things, and we can make tests for these things. We can make a test for you being calibrated at 30%. We can make a test for you being calibrated at 20%. We can make a test for you being calibrated at 20% in the summer. Now, how many tests are we going to end up with like that? Maybe 1,000. But we can average those tests so that we make a lot of money if you fail any of them. So what is forecasters? So we can kind of make up a portmanteau test that's going to make money if you fail in any significant way. That's the idea. Now, if you're a forecaster, that's the test you want to pass. So the question is, can you pass that test? And the amazing thing that we found out was that you can pass that test. If you are a forecaster, you can pass that test. Because the test is right there. You don't have to, you're not now, in a sense, skeptic is not in the game anymore because skeptic's strategy has been specified. It's this test you want to pass. And it turns out you can pass it. There's only one condition required for you to be able to pass it, and that is that strategy by skeptic be continuous. Now, is that a big demand that a strategy be... L.J. Brouwer, the famous logician, mathematician, believed that if something is computable, it's continuous. Right? A lot of people believe that. So being continuous is not such a big demand from that point of view. It's also true that all the strategies in our book are continuous. All the strategies for skeptic that we specified are continuous. We can prove all the classical theorems with the continuous strategies. So the fact that people used to think, here's an example this is something Phil David, I mentioned his name a minute ago. Phil David wrote a lot about probability forecasting and calibration, and Phil David, like all the rest of us, believed that it's impossible to be a good forecaster. The forecaster cannot beat reality and skeptic if they are colluding with each other. All of us thought that, but actually Phil was one of the people who actually wrote down why we believe that's not true. Here is why we don't think forecaster can do a good job. It's why we think that skeptic and reality can beat forecaster. It's obvious they can beat him. What do? They look at his forecasts, and if the forecast is less than a half, they make the event happen. If the forecast is more than a half, they make the event fail. That's what reality does. And skeptic bets on it happening that way. So if reality and skeptic are in cahoots, they can arrange that it goes the opposite way of what we said. What's wrong with that? Well, reality is reality. Reality can do anything he wants. But skeptic is supposed to be doing something discontinuous. This is sub-n. There should be an n here too. This says that skeptic can tell whether our forecast is exactly equal to 1/2 or a little bit less. Skeptic's strategy here is discontinuous. And if you think about it, the example absolutely depends on that. So in that sense, this example is a bad example. It depends on a false idealization that there can be discontinuous behavior in a context of real numbers. And it turns out that if you rule that out, if you rule out a skeptic behaving discontinuously as forecaster, you can beat him. If the strategy you're trying to beat is continuous, you can beat it. And it becomes because this very simple rule for making money. In order for a skeptic to make money, the amount he bets, this is skeptic's bet as a function of my forecast. I'm now a forecaster. This is skeptic's bet as a function of my forecast, and that's going to be multiplied times the 0 or 1 minus the probability. Well, what is this called? The intermediate value theorem from calculus. Right? If this function is always positive, then you make yn equal to 0 and you'll get a negative profit for skeptic. If this function of p is always negative, you make excuse me, not yn, your forecaster. Your forecaster. If it's positive, you make your forecast 1, so this is always negative. If it's negative, you make your forecast 0, so this is always negative. If it's not always positive or negative, then it crosses 0. That's the intermediate value theorem, I think. Is that right? And in that case, you choose a 0. And that also makes this 0. So you can make this negative or 0. So skeptic never makes any money. So this turns out to be something you can implement. So it's a new method of forecasting that's guaranteed to produce good forecasts. This philosophically, I haven't gotten to, so I've used up my time for sure, and I haven't gotten to Dempster-Schaeffer or Bayes. I haven't got to the applications of finance, but I have gotten to one application which is very interesting and has, I think, philosophical implications because it completely contradicted my way of understanding the world. I thought that true probabilities, that somehow knowing the probabilities was knowing something about how the world worked. Now what this says is that you can have good probabilities without knowing anything about what reality is going to do. You're playing a game against reality. Reality is completely free to move how reality wants to, but you can still make good forecasts. So that you're, and what's going on? What's going on? One way of thinking about it is, how do we make forecasts? We make forecasts by assuming the future is like the past. But actually, to pass statistical tests, we don't need for the future to be like the past. We can make the future not like. Here's the idea. The idea is that you can't, in this kind of sequential setup, and the sequential setup's important. It's online. It's online in the sense that you see the results of the previous steps before you do your next move. So what I'm talking about is only in that context. If you know some true probabilities and you can predict millions of steps in advance, that's another story. But if you only have to predict one step in advance and you get to see what happened before, then to pass the test, all you need to do is not let any trends get out of hand. Not let any trends get out of hand. Now, if the trend is that you've not been doing a good job when you said 40%, when you said the probability is 40%, the outcomes have not been coming close to 40%, you know that if you say 40% again, you're going to give reality a chance to make you look bad by continuing your error. So you don't say 40%. You say something where you've done a good job before. You choose a probability that had been working well for you before. And it turns out that's all you need to do. When you look at the details of how this defensive forecasting works, basically you just put your forecast where you'd been doing good before, which is completely natural. If you have three buddies and you play golf with Joe and bowl with Tom and play bridge with Harry, well, let me say it this way: if you're good at golfing with one of them and good at bridge with another, and you're going out with if you know you're going to go out with Harry, you want to play the game that you've had a history of beating him at, not to play a game where you've had a history of losing to him. So if you follow that, you're going to do okay no matter what happens. Even if you lose to Harry in your bowling this time, it doesn't matter because you got a record of winning before. So it only dilutes your record a little bit. It doesn't make a trend that will beat you statistically.
Isn't what these chartists doing technical analysis and financing?
Maybe so. Except that it's not actually trying to make money, it's trying to keep the other guy from making money. It's not quite the same thing. What it's doing is you're not letting the other guy run up a big amount of money against you. But you might not, that doesn't mean you're going to make a living. Yeah, it just means you're not going to lose a large amount of money. So there's a bigger story to tell, and it's in my slides about finance and subjective probability interpretation. But this is an introduction to game theory probability, and I appreciate your patience, and I'll talk about it with you about it as long as you're interested.
Thank you very much.
Can you tie this in with proper scoring? This is especially very reminiscent.
Let me see. Remind me.
So
Proper scoring means.
the simplest thing is someone is saying what they think the probability is. Say on a 0-1, you get the outcome, and then their reward is log of the outcome.
So the proper scoring rule is one where but that has to do.
It's like a
It's
list
where
of probabilities.
it makes you give the probability that you really think.
Right.
Where you spin the dial.
But that doesn't seem to be connected to this.
Well, like for the weather prediction, if you reward your weather forecaster with the log of the probability of what he or she said, what the outcome was,
Mm-hmm.
then they get the maximum reward by getting the probabilities correct.
Mm-hmm. That's not the same thing as betting against them. This is just this is more primitive in that, in a sense. But it doesn't assume that they have any. This is a rule for what the forecaster would do. So it doesn't assume that the forecaster has any opinions about what was going on. The forecaster doesn't have to have any subjective probabilities about what's going to happen. Forecaster is just trying not to be beat by a statistical test. So it seems to be a very different idea. There are some. Volodya did write one paper about the Breyer score. And in that context, you can reproduce only part, because the Breyer score is, these tests, the tests where you just bet against the probabilities are all linear in the probabilities. And so the log score, the Breyer score are nonlinear. And so you don't get everything here. Can you get something like this, like the law of large numbers out of the Breyer score? Yes, but it's already weaker. And the defensive forecasting doesn't seem to be related to it. I guess those scoring rules were kind of a way of training forecasters not to try to game you.
Exactly.
But that's not the issue here. The issue is that you're not dealing with the forecaster. You are the forecaster in this story. Yeah. Good. And it's also applies. I mean, I've just dealt with the case. I just dealt with this probability case. But of course, much more powerful and interesting is the cases of other kinds of prediction. So if you want to predict a number, that falls into the theory too, because the general, this sort of general game theoretic probabilities, I didn't stress it, I didn't give examples, but all my examples here have just been the 0-1 case. But what if reality's outcome is a real number? This strong law of large numbers generalizes to that. Your prediction, the forecasters say, just gives a price. So reality is going to say some number. It's like I buy reality's number by paying this number. So forecaster gives a price, and basically skeptic can get the difference between the price and the outcome, plus or minus as much as he wants. That's the gamble that's allowed. So it's like the expected value of a random variable. But there's no random variable. There's no probability distribution for it. The only thing being given is a price. So applying the defensive forecasting to that, of course, you've got to come out with some. I didn't go into the details. The defensive forecasting does depend upon choosing the strategy that you're betting against. This becomes kernel method. In the end, if we try to get this resolution as well as calibration, you're going to end up choosing a kernel. So the success of the method, just like other machine learning methods, is going to depend on the choice of the kernel, having a good kernel. So you can beat the strategy for whatever kernel you choose, you get a strategy for skeptic, and you can beat that. But you may not be beating the most interesting kernel. So it's another statistical method in that sense, but a statistical method for forecasting. So my point was it generalizes beyond the 0-1 case, which is interesting.
So I'm kind of interested. It seems to me like you're basing things on the fact that you've only had a finite number of steps so far, and there's only a finite number of trends that one can see in a finite number of steps, right?
Yeah.
Combinatorially.
Yeah.
I mean, in your example where you have 3 people that you play against, and you've won against A, and you've lost against B, and so forth. I mean, let's suppose the whole world changes now. Well, the laws of physics change, right? But you're still playing by the old strategy. What does it mean for a trend not to get out of hand? It means you have to constantly readjust to...
It means it doesn't become statistically significant.
Right. But you have to maybe readjust your strategy.
But that's automatic.
Right.
There's no...
What's given here, though, is basically because you've got all these finite possibilities a priori, you can always readjust your strategy in order to...
So, yeah, I mean, I guess another way of making my point is that it shows, in a certain sense, how weak the idea of statistical testing is in a sequential setup. You can beat it. You don't have to know anything about the real mechanism to beat it. The real mechanism can be changing. You don't have to know how it's changing. You can just beat it by playing against the test, the kind of portmanteau test. Now, that has limitations because, like I say, the way the world may change is that a different kernel may now be important.
Right.
And, we can guard against a countable number of tests, but that doesn't mean somebody can't think of another one. So, it's limited, but it's still... it's still a big step for me. It was still a big kind of change in my thinking about what is being accomplished by statistical testing. Yeah. And it's a change in, and it demotes for me this whole idea of objective probability. Because it means the success of statistics, the success of statistical methods has nothing to do with any, it doesn't depend on there being any kind of objective probabilities at work in the world. That's what it brought to me. Yuri?
Go back to the market.
Oh, yeah.
So suppose you have somebody who writes what's called market timing letter.
Yeah.
Let's see. You moved away from
I wanted to
the slide which was there.
Oh, there was a slide. Oh, I was going to go to the slide. I have some slides on finance. That's what I was going to.
But can we have this one for a moment? So, say for simplicity, forecaster just says whether a particular stock, Microsoft, will go up or down.
Mm-hmm.
Now, reality announces whether it really went up or down. And the skeptic tries to play against you.
Mm-hmm.
So he happened to be a particular skeptic which wants to prove you wrong.
Mm-hmm. Mm-hmm.
And so that's the skeptic
Mm-hmm.
here.
Mm-hmm.
And if you don't allow this skeptic to make money, then it's a kind of should be a pretty good forecast. You can use it for market timing. Does it make any sense?
Well, can we have zero also? Can skeptic have three? Can the forecast have three choices to say it's going to go up or down and not change? The efficient market hypothesis tells us that not changing is a pretty good. Will usually be what you're going to say.
So suppose skeptic is continuous.
But what I mean is, if you got a good forecaster and the forecaster usually says the stock is not going to change in price, that doesn't give you any way of making money.
Yes, but I'm not now interested for somebody who follows forecast. But I want.
But that's what this theorem said. This theory says we've got a good way of doing forecasting. That's the efficient market hypothesis. The efficient market hypothesis says that the market is doing good forecasting. Today's price is the best forecast of tomorrow's price. This Cournot's hypothesis, this Cournot's principle, that you're not going to make money betting at these prices, in finance is a version of what in finance they call the efficient market hypothesis. Efficient market hypothesis is the prices being given are good prices. And today's price is the forecast of tomorrow's price. This defensive forecasting is not giving you a way of playing against the market. Defensive forecasting is giving you a way of being a good market, kind of. If you think about the market, you've got we've got three players. We've got forecaster, skeptic, reality. In the stock market situation, there's only two. Because forecaster and reality are the same player. They're market. I'm the investor, I'm playing against market. In the morning, market has a price. That's the forecast. And at the end of the day, market has a price. That's the outcome. So this says, in a sense, defensive forecasting says maybe it could be a way of saying that an efficient market is possible. The fact that making good forecasts is possible.
But isn't the market timing newsletter something forecaster? It tells
They're trying to be a better forecaster than the market itself.
Yes.
That the efficient market hypothesis says that's not going to happen.
I mean, isn't there a distinction there? I mean, isn't this a theorem that's in the limit in some sense, whereas the efficient market hypothesis says, right now, today's price, period, end of story, is the right one?
No, I don't think so. Now, let me concede that the efficient market hypothesis, the literature on the efficient market hypothesis is very chaotic. There's everybody has their own opinion about how to say it, and none of them say it very clearly. I would assert that our version of the efficient market hypothesis is the first, is more, I would assert. Yeah, I'll make the argument that we have stated the most precise to date statement of the efficient market hypothesis.
In your
But
book, or is this-
in our book, that we have a very specific, because it's more precise, it's more specific. The efficient market hypothesis usually is that with the information, that the prices reflect all available information, and so that you won't make money. But what it means you won't make money is very vague. We've got a more precise concept of what you won't make money. Greetings. The precise concept is that you will not multiply the capital you risk by a large factor. It's not exactly the same thing as saying you won't make more money. It's more specific than that. What does it mean, not make money? You can make some money, but you won't make more than you won't multiply what you're risking by more than $1 million. If you have a lot to risk, you might make a lot of money. It's not contradicting that. Okay. Thank you, Yuri.
So I'd be interested